So let's start. Welcome everybody to this Wednesday morning session. And our first speaker is Naber from Princeton. He will speak about energy identity for nonlinear harmonics.
Okay, thank you very much. Thanks for inviting me. My first time to luncheon. It's lovely here. So my talk, all this is work with Daniela Valtocha. As I want to talk a little bit about, and also I'm going to carry on my laptop in a goofy fashion because all my notes are actually on this. So I want to talk about certain types of singularity formations that can occur for nonlinear harmonic maps. So when we're talking about these things, we might mean a couple of things. In fact, you might mean singularities of a fixed nonlinear harmonic map. This is a nonlinear equation. It can be singular and it can break in certain ways. You can also talk about singularities that form when you have sequences of solutions. And actually, one might think the two are more or less the same, like singularities can form in a way that will form a singularity in the limits. But as it turns out, if you have a sequence, you can actually have singularities that form on larger dimensional sets than you can actually have as a singularity itself. So these two questions are distinct. And so studying singularities that form in sequences, this is something you might imagine doing if you're studying moduli spaces, for instance, or if you're studying a contradiction argument or whatever you're doing. And what we want to understand is sort of how this sort of blow up is occurring for the sequences and how much energy gets lost in all of this when you kind of pass your limit, because the singularity disappears because it can't be singular in some sense. And there's a really lovely way of actually putting all this information together in terms of something called a defect measure. And a defect measure is actually something you could make sense of for a sequence of H1 functions. It doesn't take much. But in the case of like solutions to a nonlinear equation like this, it turns out to be very well adapted to it. And there are these conjectural pictures about called the energy identity, which say more or less that this defect measure in the limit should have a very precise form. And you should be able to count literally how much energy you lose as you kind of go through the sequence. So the first part of my talk will be kind of taking us through precise statements and what that means. And with whatever time I have in the end, I will sketch the ideas of the proof and then they kind of go into, yeah.
You say the singular set can be bigger than the limits. I was expecting like the limit.
Singular set is, no, it can be bigger. The blow up set for a sequence is bigger than the singular set in the limit is. Now that was the statement.
Like a small energy theorem, which said like if something is nice and smooth.
Absolutely, but that's the point. So it'll disappear in the limit. So this is bubbling that occurs. Like minimal surfaces don't do this. Nonlinear harmonic math do this. Einstein manifolds do this. Yang-Mills do this.
The limit is smooth, but something bubbles off.
Correct. Exactly. Right. That's one way this can happen. Exactly. This is, by the way, one problem. This energy identity for these three areas of which it appears in all three. It's the only good example I know where the proof's just totally different. Like proofs in one don't work in the other. This somewhat baffles me. But it is what it is. So let me start with just sort of introducing us a little bit to a nonlinear harmonic map and what this is. So we have a little bit of fuel for this. So for a nonlinear harmonic map, what we have is the following. We start with two Riemannian manifolds, M and N. All right. So over here, general definition. Over here, I'm going to talk about a specific example that, if you haven't seen this before, you get your head around this example at all. The specific example here is we have say a ball in Euclidean space, right? So in fact, letting this guy be linear doesn't matter that much in this discussion. It's this guy being not Euclidean that causes all the trouble. So we could have a mapping from a ball in Euclidean space into S2. And it's very convenient in this picture usually to isometrically embed this manifold inside of a bigger Euclidean space. It's not strictly necessary, but it does make life better. So here you're just viewing S2 as sitting inside R3 in the absolutely usual way. And we have a mapping. Takes a point over in our ball, maps into our sphere. And given a mapping, a smooth mapping, we have its derivative. Its derivative at a point is a linear mapping from the tangent space of one to the tangent space of the other. So all this is saying is that if we take a point and we take a vector, a direction, then by looking at a curve that goes through that vector and mapping it over, it maps to a new direction, which is the gradient of U in the direction of E. And so this literally in this context is tangent to the sphere, hence the name tangent space. So we've got a linear mapping from the tangent space over an M to the tangent space over an N. If these are Riemannian manifolds, that means we have norms here and here, and we can talk about the norm of this linear mapping. And so we define the energy as being sometimes there's a 1/2 and sometimes there's not, doesn't really matter. as being the integral of the norm of the energy squared, just like you would do in those standard linear harmonic maps in Euclidean space. And now when we talk about a harmonic map, we can basically mean one of three things. We can say it's a weakly harmonic map. So we say U is a weakly harmonic map. U solves the Euler-Lagrange equation. For this energy function. So as we take certain variations, we look at the derivative, we ask for those variations to be zero, we get an equation out of this. The equation you get out of this is going to be kind of the standard Laplacian of U. So this is kind of viewing this thing as a mapping into RK here, so just usual Laplacian in your M, but it has a correction term. This correction term is the second fundamental form of this embedding. It can be viewed more naturally if you as like a pullback connection if you want, but this is how you would do it in terms of the embedding of our N. Over on here, right, this would give down to the Laplacian of U is equal to the gradient of U squared. So we call it a weak harmonic map if it solves your Lagrange equation. We call it a stationary harmonic map. I'm going to give a slightly line definition that I think is better for intuition, and then I'll say precisely what it is. A view of the critical point. And we say it's a minimizing harmonic map. If with respect to like local and bounded variations, compactly supported variations, whatever, if you use a minimizer. And the fascinating point about all this is that if you're talking about a linear harmonic map, so this is just R over here, all the same thing, doesn't really matter what you mean, right? If you solve your Lagrange equation, you are a critical point and vice versa. And if you're a critical point, you're actually a minimizer. That's not too hard to see for linear harmonic maps because it's like a non-negative quadratic function. If you have a critical point, what do you have? You've got a minimum. That's all you can really have when you do this. That's the cheap answer for it anyway. In the case of the nonlinear case, all three are different. That these two are different is not surprising, maybe. Being a critical point doesn't have to be a minimizer. There's all kinds of critical points that are going to live around in this world. That solving the Euler-Lagrange equation is not the same is much more interesting. In some sense, you're not capturing all the variations that you can have as a critical point. You're actually missing an equation here. It's called the stationary equation. And the stationary equation is basically clutch to almost everything you do in this business. So the moral takeaway, even though I'll hide it under the rug for most of what we talk about, is that being a critical point of a functional is more fundamental than solving an equation. You get more data from this. So from like a regularity point of view, solutions of minimizers are smooth away from codimension 3. This is Shane and Uhlenbeck. Stationary are smooth away from codimension 2. This is Bethiel, also a very nice proof, I think. But if you're a weakly harmonic map, you can be discontinuous everywhere, right? They're like legitimately, it's not just a technical point, they're legitimately different things, all of these things. That's an example by Tristan-Riviera. So this is what we mean by a weakly harmonic map. And if I was giving the colloquial version of this talk, I would now give you a bunch of examples of harmonic maps. We will work in one example, but we'll do it just in the context of what we'll be talking about, which is this sort of blow-up test will be occurring. That way I have some time to talk about proof at the end of all this. So all that set up, let's talk about blow up and defect measures. So again, I'm going to follow the same sort of strategy as over there. I want to talk about a general setup over here, and I want to talk about a very specific example of it happening over here, the easiest example possible in some sense. So the setup that we're talking about is that we have a sequence uj from an n of stationary harmonic maps. We always assume stationary, otherwise nothing is really true. And they have to satisfy the mean real assumptions. They have to satisfy a uniform energy bound. energy going to infinity, especially non-locally. I mean, if it's like locally going to infinity, this is a different business. One would think you could say something, but right now there's zero to say about these things. In the Ricci case, you can say something about this because there's other rigidities, just as an offhand remark real quick, but there's no analog for other situations. There should be. It's called splitting theorems in that context. Those don't require energy balance sense. So we start with our sequence of harmonic maps over here. What we want to do is take limits of these things, kind of makes sense. So given that they have energy balance, what we can do is take weak limits in H1. The H1 weak limits to some U, and that itself is going to be a mapping from M to N in general. And we want to understand what goes wrong potentially in the sequence, why this weak limit isn't a strong limit, why the energy of this guy might actually drop from the energy of this, and what kind of blow up can occur. So let me first write down an actual example of a sequence like this. So my setup here is going to be, I'm going to have some U epsilon. I'll have a one parameter family instead from R2 into S2, which I'm going to identify as CP1. So if you haven't seen it, this is really quite nice. So we can identify S2 in the following very convenient manner. We can do it as pairs of complex numbers. Z1, Z2, not both zero. So basically you're going to look at C2 minus the origin and mod out by C, like it's identification of complex lines. But what we're really saying is that there's an equivalence relation on pairs of complex numbers, so that if we multiply them both by the same thing, we call them equivalent. And if you think for a few minutes, then this actually gives you S2 in higher dimensions, it gives you CPN, and that happens to be the same as CP1 and S2 happen to be the same here. So I'm going to identify my S2 through this sort of complex coordinate chart here. And with that in mind, I'm going to define my sequence of mappings as follows. My U epsilon of Z is going to be the equivalence class of epsilon Z. So we'll fix the epsilon there. So let's draw a picture. Try to understand what happens. Oops. In particular, I'm going to really want to understand what happens as epsilon goes to zero in just a couple of minutes, and it'll be fun. So, okay, so what's this map look like? So first off, let's look at where the origin maps, because that's a nice, easy thing. The origin, so U of 0 maps to epsilon 0. Epsilon 0 is the same as 1, 0, so I can multiply both by epsilon inverse. 1, 0 is always going to be the south pole. So no matter what my epsilon is, this point maps to this point down here. My north pole will be 0, 1, just as a sort of a basis, and then like 1, 1 will be kind of over here, for instance. And sort of get a picture of what points up here, how they correspond to points down here. So fine, that point always maps to this point. Now let's look at this ball of radius epsilon here, and let's see what that maps to. We've got that guy there. So in particular, let's look at the point Z equals epsilon. That's a nice easy choice over here. Z equals epsilon, that's epsilon epsilon, which is the same thing as 1, 1 when I multiply by epsilon inverse both times. So that is always this. And in fact, what you're seeing then is that this ball of radius epsilon is just mapping to the lower here. So in some sense now, how are these mappings changing as epsilon goes to 0? For 1, I'm just basically mapping the ball of radius 1 to the half sphere, and the rest of it kind of maps to everything else. Right? This is basically a diffeomorphism away from this guy. It's closing up around it, right? But as epsilon gets small, the diffeomorphism is mapping the ball of radius epsilon to the half sphere. So it's wrapping faster and faster and faster. And if I were to take any point out here, some Z, which is not 0, then what we get is that the limit of U epsilon of Z, this is not 0, is what? So as epsilon goes to 0, this becomes 0 Z, which is the same as 0, 1, which is the North Pole. That is the limit mapping the constant. Right, so away from this smaller and smaller balls, away from the origin, you're just converging to constant map of the North Pole. Let's see. So there's an example of, oh, and it's probably worth mentioning, by the way, that all these maps, fun enough, energy independent of epsilon, it's actually, if my computation was right, because I did this like 3 years ago and I haven't redone since. It's APOD. Why are they all the same energy? This is something you can do yourself. That's kind of fun. If these are all nonlinear harmonic maps, if you take my word for that for a minute. So they're holomorphic maps between Taylor manifolds that are actually always harmonic. That means that the derivative in epsilon has to be a critical point, which means the rate of change of this is 0, which means whatever the energy is at one point is going to be the same everywhere else. So all you actually have to do is compute it. One thing, you see the energy is always the same. Yeah, let me check anyway. Okay, so what we see here is that we have a sequence of nonlinear harmonic maps. They have energy bounded by 8 pi, and they're converging to a smooth. So they're smooth harmonic maps. They converge to a smooth harmonic map. The smooth harmonic map in this case just being a constant, but they're not converging smoothly. All right, that something is funky happening. In particular, we can see quite clearly something's funky happening right here at the. So how do we capture that? What's happening, especially in a general sort of scenario? And there's a really fun way to do this, and it's called the defect measure. So the idea is, let's look at the energy of this guy. General now. But, this is a nice L1 function, but I'm not going to view it as a function. I'm going to view it as a measure. So let's multiply it by the volume form and view this as a sequence of measures. Because then I can limit this as a measure to something. So as a measure, it will limit. And what it'll limit to actually is the energy of our limits. V into U squared, VG. But if the energy here drops from the energy of this, like note this example here where it's 8 pi and then 0 in the limits, then we can't lose mass in probability convergence. That's why we like to limit as measures. So there's something else being here, a plus mu. That mu is our defect. So it's capturing exactly where something went wrong in this convergence. Like you're not converging even in H1, much less smoothly, away from wherever this thing has support. And if we look over here on this example, we get to is, well, what's happening? Geez, this is just a opaque volume form on the Euclidean space. Well, we see that's away from the origin. What's happening is you're just mapping smoothly to 0. You have 0 energy. All of your mapping in some sense is being contained inside smaller and smaller balls around the origin. So this 8 pi of energy, it's being sort of squished into smaller and smaller neighborhoods around the origin. So in the limits, it's just a Dirac delta. It's 8 pi times the Dirac delta of the origin. And from this, we've at least captured the fact that, well, we clearly couldn't have had smooth convergence for that to happen. Right? And we've captured exactly where the blow up is, namely the origin. And we've captured exactly how much energy got lost. Namely 8 pi in all of this.
In general, this might depend on the subsequence in principle.
Oh, sure, absolutely. Yeah. A priori, I mean, you pass subsequences and subsequences and subsequences before you say anything.
Then maybe after.
Yeah, I'm sure you can even rig up a fake example where this happens for silly reasons. Once you get convergence of one, you'll probably get conversions of others. But you can certainly flop back and forth in really small guys, and you can't tell until you zoom up enough. So let me point out one thing about this, that's a good rule. Where this went bad was at the origin. That is a point inside of R2. It didn't go bad everywhere. It didn't go bad on some Cantor set. It didn't go bad on some we're looking one-dimensional set. It was a point in R2, which is to say a codimension 2 set. Right? And that is a general phenomena that was really proved by Lin. I'm going to make a statement of a theorem real quick. So in general, Feng-Wall Lin proved a really lovely result about this defect measure mu. Theorem. Lin. Oh, says here amazing. Right. J, sequence of our stationary harmonic maps. Energy bounds. And let, after passing to a bunch of subsequences, if you need to, okay, go to not weekly page 1, and the energy measures. Corresponding energy measures. I'm rewriting this all on purpose so we all have time to absorb everything that's being said again. Plus the defect measure that's occurring over this. Then, well, what improves is that this mu, and I'll make the statement first, and then I'll try to make it a little bit more precise afterwards. And n minus m minus 2 m. So the m can correspond with the m, and the n's can correspond with the n's. It's an m minus 2 rectifiable measure. So some remarks on this. So I'll say it in words and then I'll make a statement. A set is rectifiable. So n minus 2 rectifiable. You should think of a rectifiable set if you don't have a feel for this, though I think most of us probably do, but still, that's okay. As being an n minus 2 manifold with holes. So that is to say you build these things exactly the way you build a manifold. You have Rn minus 2. You have sets inside that, you have charts inside your space. It's going to cover your guy, maybe up to a set of n minus 2 measure 0 is usually what you allow here, and that's that. So it looks just like an n minus 2 manifold. The main difference is no one says that these charts have to be open. They can't just be measurable subsets of Rn minus 2. And so from an analysis perspective, they tend to be just as good as manifolds for most points of view. But they allow holes. This is oftentimes necessary. A good example of this would be like a one rectifiable thing with maybe a crossing of two curves like this. So one manifold, one manifold, one manifold, one manifold. That point in the middle is not a one manifold. Something slightly more ugly looking would be like this same guy, but now take your favorite subset of it. Basically, any subset of that, measurable subset of that, also counts as being one rectifiable. You could have holes scattered throughout in addition to the weird points that it actually looks. But it's essentially covered by one manifolds in this way. So in particular, what being a rectifiable measure means is that the support mu is contained inside an n minus 2 rectifiable set. So think n minus 2 manifold if we're not comfortable with it. And mu is going to be the Hausdorff measure on this set. But you're going to integrate something over it. It's not going to be just a Hausdorff measure. It'll be some ELX. And the that way. This is the energy density. The defect measure. And this guy here is really representing how much energy got lost at that point. So if we come over to our example over here, we have our two-dimensional harmonic maps. We're moving to an n minus 2, which is zero-dimensional rectifiable set, which in this case is just a point. Call it a zero manifold if you want. It's actually pretty nice. And what you're integrating is the Hausdorff measure over it. That's the Dirac delta times the energy density. That's the 8 pi. And as we notice here, that was exactly how much energy we lost. It was 8 pi. And that's what disappeared when we went through this process. So it's measuring the energy lost in all this. And let me provide one relatively trivial example of that isn't two-dimensional, but it's basically going to be a copy of the two-dimensional one. But it'll let me draw a picture that we'll come back to later when I start making other line definitions, so that we can at least have a sense of what's happening. Let's get on with it. Example. Just to give an example that isn't two-dimensional, see how this happens when m is bigger than 2. the absolute dumbest thing in the world you can do here is I'm gonna pick U epsilon from R M, which I'm gonna write as R M minus 2 plus R2 into S2. My mapping U epsilon of X, Y. So X is in R minus 2, Y is in R2, just like my splitting. It's simply going to be epsilon Y. So that is to say, I just took this example over here. I crossed the domain by R minus 2, and I ignored those variables entirely. Right? This is still going to be a nice sequence of nonlinear harmonic maps. The way you should view it this time is here's our L, which is like R minus 2 cross the origin. Then for each slice, through one of my points L, what we essentially have is much the same picture here, where we have on the ball of radius epsilon in this two-dimensional slice, the mapping is just looking like that mapping here, and that's independent of which slice I take. So now if I do the same game where I look at U epsilon, well, it'll limit to a constant once again. So that'll be 0, 1, or 1, 0. 0, 1. 0, 1 into the constants. But the defect measure in this case doesn't limit to a direct delta. What it limits it to is 8 pi times not just the value of that point, but the integral along this line L here, right? So that is the Hausdorff measure along L, somewhat trivially. And then this epsilon here is kind of being like that. So we have our mapping is looking very constant up here, and it's looking very much like it's wrapping around half the sphere down. If I start to erase this, stop me. And I want to point at this later. Okay, so then now what I'm going to do is give you the one real definition of this. So I want to talk about how this situation over here is going to generalize to the context over here. And to do that, I need to introduce blowups and bubble maps. Both of these things are well worth knowing. If we're not, I mean, either we're familiar or we're not. And if you're not and you're here, you should be, because they appear in virtually all geometric PDs. So in this context here, I'm going to give a definition. The definition is going to be more or less independent of being a harmonic map, but it's only going to be really interesting for harmonic maps. So let's let Uj be some sequence of mappings from some M to N. We're thinking harmonic map, but whatever, it's any sequence of let's say H1 mappings for whatever. Let's let P, so n-dimensional, be a mapping from Rm into N. And then we're going to make the following definitions. So definition way. So I'll write the definition and then we'll go over here and say what it looks like in that particular example. We call F hat, which is a mapping from Rm into N. So no matter what this space is, this will always be Rm. Blow up. At X and M. If there exists a sequence of points, Rj going to X, in all of our examples, Xj will just be X. We're fixing the point, but in principle, you might have to trace your way near it. And radii, Rj going to 0, such that U hat, I know say F, such that U hat sub j, which is defined to be Uj of Rjy plus Xj. Say J of Y, so we're clear about variables. Think about Euclidean space, otherwise use exponential coordinates here. Converges the U hat, which is a mapping from RM. Yeah. So this deserves some comments. So what is this definition over here? So over here we have our sequence of maps U epsilon. Now, what you're doing with the points X and the scales RJ is you're zooming up on the ball of radius RJ around X. You want to know what the map looks like at that point, and you want to look and ask if it's non-trivial or not. So here, the good example to pick would be we let our XJ just be the origin for all points. We're going to let our, in fact, we'll call this X epsilon. We'll do it once for each epsilon. We'll let our R epsilon be epsilon. So you're trying to pick scales in principle where you think something is going wrong on that scale. And that scale is the obvious choice here is epsilon. What I want to do is take this ball of radius epsilon and I want to zoom it to a ball of radius 1. That is all this does. That takes your map UJ, which is, and it makes it a mapping so that the ball of radius 1 here corresponds to the ball of radius RJ here. And so you've zoomed it out. So if we look at our U hat, hats for like blow up here, epsilon of Z is my variable. Then this is just equal to epsilon and epsilon Z in this particular case. And I can multiply both sides by epsilon inverse because it's equivalent, which means it's just 1Z. So what that means is that once I take this guy and I rescale it to a ball of radius 1, in fact, the mapping becomes the same map for every epsilon, as it turns out. Not a constant. You see something highly non-trivial happening here. There's like U1, essentially. Not essentially, literally. This guy, as epsilon goes to 0, it obviously converges because it's independent of epsilon. And it converges to 1Z. And so that's what we call our blow-up at this point. So when we rescale out, in some sense, this is almost a cheat example. Like how does it really work? I take my U1, I scale it down to get my U epsilon, and I'm scaling it back up to get back there again, right? But nonetheless, the fact that you can do that without losing harmonic map is the only point that's maybe really does need to be introduced. Otherwise, it truly is cheating. So, okay. A U hat is a blow up. If we look at a sequence of zoomings, we rescale those zoomings and we get a limit out of this. And this is telling us because the RJs are going to 0, that something funky happens. Like my quiz for my colloquium talk would be what happens if these are all smooth, uniformly continuous functions, for instance. They're gradient bounded by 1. Like what does every single blow up look like? And the answer would be a constant. So if I take any continuous, uniformly continuous, and I zoom a small ball, what's it look like? Looks like a constant. So in some sense, this being not a constant is telling you you're not continuous. Something is going wrong. All right, so that's what you're looking for. So the fact that our limit here wasn't a constant, that's why there's a problem. If I picked any points here that wasn't the origin, played the same game, I get a constant. Yeah.
Which sense of the convergence is?
Let's say if these are all in H1, then they'll be in H1 weak. Whatever's reasonable to your setup, and for us, that means H1 weak. Yeah, point number 2, just to really emphasize, no matter what manifold this is, this always gives you a mapping on RM, right? Because what is a manifold by definition? It's something that if I look at small balls, it looks like Euclidean space. So if I take that limit, all we have is a mapping on Euclidean space. So it's worth pointing out that even at this stage, we've gained a little bit in the sense that curving here goes away. We at least have something on a nice Euclidean space, which feels better if nothing else. Definition 2, we call B, which is a mapping from RM, which I'll write as RM minus 2 cross R2 and to N, a bubble map. F, so this is just a fixed map. Ignore the scenario, we'll combine the two in definition 3, but right now it's its own definition. It's just a mapping from Euclidean space into N, and we're calling it a bubble map. If we can find coordinates so that we can write R minus 2 cross R2. And if this B of XY is actually just a B of Y, which is a finite energy harmonic map from R2. that is, there are m minus, it's really a two-dimensional mapping, despite the fact that it's being written on an m-dimensional space. M minus 2 of the variables don't count, it doesn't see them at all. And for the other two variables, you're actually just a two-dimensional harmonic map of finite energy. Note, by the way, these are all bubble maps stupidly. They're just mappings from R2 and into there. But in particular, our limit here is a bubble map, which is the point I want to emphasize. If I had done something like restrict the domain to B1 here, just because I felt like it, these wouldn't be bubble maps anymore. But the blow up here would still be a bubble map, just sort of as a reality check. And our final definition is that we call B a bubble of uj at x if it's a bubble map. Which is also a blow-up map. So we call it a bubble of uj if there's a sequence of xj and going to x and rj going to 0, so that when we blow up the u at those scales, we get a limit map u, and if that u just so happens to be a two-dimensional harmonic map, we call it a bubble map. By the way, why the name bubble? So if it's a finite energy or harmonic map from S2, then you can conformally change R2 to S2 by closing it up. And there's a removable singularity theorem that says it extends to a harmonic map over all of S2. Hence, it's really like a harmonic map from S2 and into your space. So hence bubble, which by the way are the same as minimal surfaces from S2. So really these bubble maps are really like two-sphere minimal surfaces that are occurring in a sequence. Okay, so that is about it. Those are the hardest definitions. If we're good, we're good. Last point I'll make is that in this sequence here, this is exactly what happens, right? We have a sequence through epsilon. We get our blowups on scale epsilon around 0. They converge to a 1z. That's clearly still a harmonic map. Therefore, there's a bubble map at the origin for RU epsilons over here. And the last point I really want to make before I state the energy identity conjecture in a second is the following. This 8 pi that's in front of our Dirac delta here, this energy loss, it just so happens to be the same as the energy of this bubble map. And that's not random. So the amount of energy you lost corresponded exactly to a bubble map at that point. And the energy identity conjecture, which I will state now, basically says this always happens. Well, I gotta think my numbers. So the energy identity conjecture. Says that if we're in the setup, UJ sequence of stationary harmonic maps with energy balance. And after passing the subsequences, we have that there's the defect measure. Volume form there. Mu with by Fong Wall Lin, we have that this is E of x times the integral over some n-2 rectifiable set S E. Then there exists a so far that's a theorem, and the last part's the conjecture. Then there exists a finite number. It'll have to be uniform as it turns out. I don't have to shove that in there, it'll be automatic. Finite number. Then for almost every x inside the support of this thing, there is going to exist a finite number of bubble maps. Two-dimensional harmonic maps. B1 through in at X such that the energy density of this defect measure, the amount of energy you lost, is exactly the sum of the energies of the maps. So maybe a few words about progress on this. Yeah.
You say anyway, but this problem may not relate to signal. This if someone said either all of them you can find.
It'll sort of necessarily need to be all of them. And somehow any other one you find will have to be equivalent in the sense that there'll be other x's and other radii whose ratio don't go to infinity, so you can capture this. So if you missed one in some sense, then you couldn't have had equality here, as it turns out. So it'll have to be all of them in some sense. But you got to be a little careful about exactly how that is. You might actually come from different directions and either get one or two, because they might actually combine or not. So it's you got to be a little careful, but they're essentially all of them.
And these EBJs are quantized.
What's that?
The EBJs are quantized.
The BJs. If the target is smooth, absolutely not. In fact, you can write down an example where it can basically be an entire Cantor set of energies. If the target is analytic, then I would say conjecturally this is true, but this has not been proved. It's definitely true for the sphere. You can write them down. Let me mention just sort of in words real quick, progress on this over the years, just so I'm giving all the fair stuff. So this originally arose from surfaces, kind of like the situation we were talking about over here. So it arises, especially when people were talking about these moduli spaces and Gromov-Witten invariants and things like this. Also for pseudo-holomorphic maps, so that was sort of the context. So for pseudo-holomorphic maps, which is like stronger than being a harmonic map in some sense, from surfaces, so two-dimensional spaces over here, then this really follows from work by Uhlenbeck and Taubes in the 80s. And for general surfaces, two-dimensional surfaces here that aren't pseudo-holomorphic, they're actually harmonic. This was proved by Parker and Yost in the mid-90s, I guess. Also, there's things like approximate harmonic maps that it was proved for by Ding and Tian, and also Lamb, who sort of generalized a lot of the stuff. For general dimensions, I would say the first really good results for general dimensions here was by Lin and Tristan Riviera. What they proved is if the target was a sphere, they proved this was true. And the way they proved this was true is that they were able to prove something which they conjectured to be true in general, called the W21 conjecture. They could prove any of these mapping that the Hessian lived in L1. And it turns out, because of fun Sobolev embedding stuff, so by Sobolev embedding, you kind of get that the Hessian living in L1 will kind of be enough to put it into L2 on the slices. It's a little bit better than that, and that little bit better lets you capture kind of what you're looking for in this case. So they proved it for target spheres, and actually they proved it in general if you had this Hessian bound on guides. It was proved by triholomorphic maps by Bellantini and Tian, and also the corresponding version of this conjecture holds almost verbatim for Yang-Mills maps. And it was proved for instantons by Uhlenbeck, and in dimension 4, which is the corresponding notion of surface here, the critical dimensions 4 there, not 2. It was proved by Tristan Riviera in general. And then I guess about 5 years before we proved it for harmonic maps, Daniele Valtorta and I proved it for Yang-Mills. And our thought was same proof, right? It was just copy it over. And it turns out to fall apart entirely. It's not just that it's hard to make work, it's wrong. The steps of it actually are just wrong in the harmonic map case. So Daniela and I proved it for harmonic maps, but the proof here is actually entirely different, an entirely different set of tools. So in particular, in the 7 to 10 minutes I have left, let me say a few words about. And now is where we start going quickly and sketchily, and I'm just going to try to make sure that buzzwords kind of appear. And if you happen to be an expert in the area, you'll follow. And for the rest, I hope I get a general gist of what we're going to talk about. Okay, so for the proof of the energy identity that Daniela and I gave. So the starting point of it is the same actually as for Yang-Mills, and actually the same as for a lot of setups here. So you have something called a quantitative annular bubble decomposition. So actually this thing holds for all K, not, we're going to apply it into 2 dimensions in just a second. But it basically says that any solution can be broken. It's basically a quantitative stratification thing. It says that any solution can be broken up in a very quantitative way and into pieces where some of those pieces are going to look like they're K-dimensional solutions, in fact. So even though you're on an n-dimensional space, they actually look like they're solutions in a lower dimensional space. And they're going to be connected together with annular regions where you're actually going to look like you're a solution with a lower dimensional of an even lower dimensional solution that sort of connects these would-be bubbles that kind of go on here. In the context of 2 dimensions here, what this says is that we can break up into regions, any solution whatsoever. And what will happen in these regions, I want you to keep this picture in mind for this explicit example, is that you'll have some regions here that basically look like 2-dimensional harmonic maps. You'll have a small content set that you know nothing about in this decomposition, but for all effective purposes, you get to chuck that because it's of such a low kind of control that it doesn't matter. And connecting these regions that look like 2-dimensional solutions, so you should view each of these little balls here as kind of looking like one of your 2-dimensional solutions here, but maybe the radii vary. The bubbles might go in, they might go out. There actually might be singular points, so maybe there's actually a 0 in the middle here where they kind of go down to and they come back up. You can do all kinds of funky things. But they're kind of just waving in and out of 2-dimensional solutions. And then up here in the annular region, actually, it's looking like a constant in this case. It's looking like a smooth constant solution. So your U is, here's your annular region. Your U is basically equal to a constant here. And in these regions here, your U is basically equal to a bubble now. So what we really prove, is sort of an effective version of energy identity. Everything we do is affected by sort of nature. And it says that whenever you sort of start to look like close to this scenario here, then if I start slicing by 2-dimensional subspaces and I restrict my map, then it's going to turn out that if we take this U and we restrict it to a 2-dimensional harmonic, 2-dimensional plane here, then it's going to look close in an energy sense to a 2-dimensional harmonic map. And in some sense, this is a stronger version of what's happening over here. And the main thing that really has to be proved in all of this, when you're in a setup like this one over here, where your bubbles are quite small and you've got like, you're looking very close to a constant. Ironically, this region here, the annular region, where you look close to a constant, you're smooth, like there's nothing really happening. This is the trouble region. You need to show that the energy on one of these annular regions is small. And that's the real problem of all of this. The reason that's not clear is that if I look like at a ball here that kind of on some scale, kind of any scale in terms of the distance to our I mean, let me draw a better picture here. This should be like you should be viewing all these bubbles here as being kind of living on some n-2 submanifold, but maybe not a plane. So they're kind of all centered on this T here if you want. So if I look at any ball around here, the energy on this ball is always small, but there might be an infinite number of scales here. You can't necessarily sum that up. So you certainly can't say that the energy on the whole annular region is small. So this is what you really have to prove in the end. And to do that, what we're going to do is we're going to take a point, X in here, and we're going to decompose first the energy into 3 pieces. So I'm going to write this energy. Do this anywhere, but it only really makes sense on the annular region here. I want to care about the direction L, where you're looking like you're invariant in that direction. Right? So here we've got this sort of defect appearing. It's kind of looking like a constant plane in this direction, satisfying a right convergent direction. This L is supposed to be that direction. So let's look at the direction where the energy is basically a constant. I'm writing it as L sub XR because actually as you kind of get closer and closer to T, it could move around as you're going down. For higher K, it can do that actually. Here you can be a little bit more restrictive. So let's look at the energy in the kind of invariant direction. And then for the 2-dimensional directions that are left in the perpendicular direction, let's break this 2-dimensional part of the energy. This is like the energy in the bubble harmonic map directions into 2 pieces. So using here that the slice is actually going through RT, let's break it up into an annular direction So this is this is a two-dimensional, this is a little bit better. So this is like a two-dimensional plane. So my annular direction is this, and I have a normal direction is this. So I've got a radial energy with respect to this two-dimensional plane, and I've got an angular energy with respect to this two-dimensional plane. Now we want to estimate all three of these things independently. All three of these components basically require a different idea. For the L direction, we prove something kind of fun. We prove that actually the L energy, the energy of U in these sort of splitting directions as you're going down, isn't just an L2, it's actually an L2 log L2. You actually get an improvement on this. So this L energy here actually has a bound on this, but only in the annular region. It's very important that we actually restrict the annular region. You go below that, and then you'll lose control of this. So you get this log improvement on the L energy here. This is shockingly easy to prove. It was surprising to us it wasn't in the literature somewhere. I think the big reason is that to see it, you need to think in terms of annular regions. When you think in terms of them, it becomes very natural to estimate in a certain way and it pops out. If you don't think that way, it's maybe, you never even think to compare these L's as you go down scales because things don't get comparable on the different scales quite so well. So this is basically enough to show smallness for the L. This is like, a bump up of energy. One can maybe imagine there's a million ways to go from here to smallness once you actually do this. For the angular energy, the part that's in like the S1 direction of our two-dimensional plane. So as I said, the Yang-Mills proof for energy identity doesn't work here, it fails, but it turns out to work for this component. So all of that proof, if you apply it here, that'll actually give us the estimate here. The real trouble is this guy here, and we spent about 2 years on this. So there's a cheap proof for this that we put at the beginning of the paper that's almost misleading. If we assume that these bubble centers, like where these things are kind of centered at down here, was a straight L like this, then what you can do is you can use the stationary equation, this extra equation you have that because you're stationary, pick a clever vector field to pair it with, and what you'll get in that context is that this energy is actually controlled by these energies. Done. That's it. Once you have these two guys, you have this guy. Now, the problem is that this thing is moving around. And if you compute the errors for the energy addition that you're having from the movements, it's exactly going to be equal to like bound by a constant times the energy of this annular region. This is useless. And so if you knew the energy identity, you could say this component was small, but meh, you can't use this for much. The fix for this is the following. 1 minute. I think I'm only 2 minutes away. Everything here is going to solve an equation. The L's here, you could actually take them to be relatively constant in this case, but you don't. You make them the best possible L's everywhere. The T here, most importantly, you don't pick to be a random T. It's going to solve an equation. In some sense, whenever you slice these two-dimensional slices, it's going to look like the top of the Gaussian, that's kind of the energy distribution on that set. It's going to solve something on each of these sets. And likewise, then, the angular parts and the end parts will solve something. They'll all solve equations. And what is simply a miracle of the math, like there's no other explanation for it, is that when you look at the errors that occur, when you're trying to estimate this guy by these guys in the stationary equation, every one of the leading order parts is one of the Euler-Lagrange equations here, plus something small that you can control. And then boom, you're done. All right, so finding that equation to get the Euler-Lagrange equations to kill all the rest of that, that was what we spent most of our time on. And okay, that's the proof. Thank you.
Question?
Hey,
So these scales, as you move along T, they can be quite arbitrary.
they can be quite arbitrary. You can assume they're Lipschitz for almost stupid reasons, in some sense locally, but that's about all you have to.
So,
They can go to zero and come back up and like find. I mean, if you have singularities and the non-singularities, you can see from that it can't be better than Lipschitz in some sense. They'll go up and down.
When you say that, you mean like
Oh, you can definitely construct examples. In fact, you can do a really fun one with holomorphic maps, where it's your T here will be like a two-dimensional plane, And you can make the singular set, which will just be points in this case. So this is on C2, so these are like codimension 4, but you can make it as dense as you want inside this thing. So in the limit, you'll actually get all of T, but you can make the actual singular points as dense as you want inside of T.
For the scales.
The scales have to vary in some, in that case, they'll vary by a holomorphic function in some sense. But they have to vary because they're going up to something and then going to 0 and then going back up and down. So in particular, their log, which is really what you want to control, is not. Like it's all over.
So that's Hessian L1 conjecture.
We do not prove this. No. So for the Yang mills, we prove that. Actually, we prove it. We prove the Hessian, the corresponding version of the Hessian L1 and the energy idea at the same time. Like basically, it's the same tools. It's not one from the other or anything. They just both follow at the same time. Here we lost that. We've lost the W21 conjecture out of this.
Does this give anything about the singular set at the end, or like it's support of the feedback measure satisfied some equation?
This is the right question to ask, but this is not so clear. So I think if you're looking to prove that, I think this has to be the way to go. Because the problem is that one of the reasons we got stuck for a long time is you try to do something like that. You set up an actual equation that you want your T to satisfy, and there's no chance. In the limit maybe, but the errors correspond to that. There's no chance. So you can set up a very natural equation in the end, and I would think any equation you do have in limit would have to follow from this. But you know that this has to be an extra step, which we dropped this problem afterwards. We got really sick of it. So I know we just haven't returned.
Is there conjecture?
I wouldn't go that far, especially if the target is smooth. Because if the target, I mean, this is maybe a problem. If the target is smooth, I might suspect you can get Cantor set singularities here in the limits. At which point, one gets very nervous about saying it solves an equation. What's that? If you assume analytic, one might think that there's something floating around here, but I would need to think. I mean, minimal surface is usually the guess one makes because there is a stationary equation here, in fact. So it's not inconceivable, but I think a first step toward that would be quantization, because you've got to make sure that the energy isn't fluctuating, because that would contribute to this equation.
Let's see if we get
What's that? So the problem there is that you're basically asking for a Lojasiewicz, where you don't have a uniformly C2 bound. You have bubbles and bubbles and bubbles and bubbles, and you're going to singular limits. So I would say morally, yes, that's what you have to do in the end, but you need to make it work in a very singular situation. This is strictly weaker. Yeah. Essentially, what our ability to go from these two, we can basically control the same control we have in Yang mills will give us kind of Hessian L1 in these directions. But when we go from those to this, we've lost it from this equation. We haven't.
Right, but you can't try to these things.
Oh, I imagine it's true. It just doesn't follow from this. It'd be much more interesting to me if it was false, but I imagine it's true.
Perhaps I missed the detail. Where are you using again the stationarity?
Absolutely everywhere. I hid this under the rug for everything that was said. So, the stationary equation gives rise to a monotone quantity. This gives rise to regularity theory. Without this, you can't even say you look like a constant in this neighborhood. Like everything's gone.
Point of view of each component in the angular region.
Okay. You can set up a different stationary equation than you do for or apply it differently than you do for the monotone quantity to try to control this energy by these energies. And in the case where it's a straight L, you can do it just straight away. And it was the error terms that end up being on the same level as the energy itself that caused a lot of our problems. The wiggles.
Any other question? No, so we have plenty of questions, so let's thank